All right, welcome to week 10. It's the first day we're going to talk about geometry. Let's go ahead and get started. So there's some basic kind of overall strategies for doing geometry problems. And a lot of it's visual, a lot of it involves pictures. So I'm going to go over kind of the basics. So the basic strategy here with geometry. All right, so the basic strategy is this. Right? We always want to draw a picture. If it's possible to draw a picture, we draw one. There sometimes is one given to you, but if not, a lot of the times drawing a picture is going to help. Okay? And you want to mark or fill in what you know. So they'll give you information, or maybe you're supposed to know information, but you want to notate that. You want to write that on your picture. Okay? I know that this side and this side are congruent, so you'll mark that. Okay? So that you can see what's going on a little bit better. Then, of course, you're always allowed to add stuff. So you can add line segments, you can extend lines, you can drop altitudes from a triangle to that picture to help. So we're going to we can add segments or extend lines. Basically anything that's going to help you really see what's important on the picture. Drop altitudes. So what I mean is if we have a picture like this, and it says something about what is this angle compared to this angle. Well, we can extend these lines out if we need to, okay, to see it as maybe parallel lines with a transversal. We'll talk about that later. Also with a triangle, you can drop what's called an altitude. That's that perpendicular line there to the ground. You can drop that line down. So you're adding to the picture sometimes, and that's going to help you kind of make sense of the problem. All right. So one thing you're going to have to be able to do in geometry type problems is you're going to have to set up an equation. Okay, you have to be able to set up equations. And they're not terribly difficult. You just have to kind of get into this thought process of how it works. So let's say, for example, we know that angle 1 is equal to angle 2. Okay, and they tell you that angle 1 is 3x plus 6, and that angle 2 is negative x minus 12. Okay, if they're the same, if they're congruent, then they're equal to each other. Well, it's easy to write an equation. You just say that angle 1 is equal to angle 2. Now, of course, that equation doesn't help you, but what you do is you replace what angle 1 and angle 2 are. So you fill in these blanks with the expressions that they give you. That's what I mean by setting up an equation. You've got to be able to do it. If two things are equal, this equals this. Easy as that, okay? Sometimes they'll say things like angle bisector, right? Anything something is bisected. If it's an angle or a line segment is bisected, it breaks it into two equal parts. So for example, this angle is divided into two equal parts, and those little lines are how I describe in a picture, how I show that they're equal. Well, I would just say that whatever this is equals this. I put the equal sign in between there. If they're equal, then this equals this. And usually you're given expressions to be able to do that. Okay. Another example is if things aren't equal, things aren't always equal, but sometimes things add to equal 180 degrees. That's very common, especially with triangles or supplementary angles. So if two or three things, let's say three things, there's three angles in a triangle. One angle is 3x, the other one's 2x, and the other one is 5x plus 20. If I have a triangle and I know that those three angles add to be 180 degrees, then I put the first thing plus the second thing plus the third thing equals 180. And there's my equation, okay? You got to be able to do this. This adds up to be 180. Well, then that means that this plus this equals 180. There's your equation. You're going to have to be able to solve that, of course, too, but really just setting it up is what we're after here. All right. Third kind of main example that you'll see is you'll have these little line segments, the big line segment here broken up into little pieces. So maybe the big part is 12x plus 60, and you know that this is 3x minus 10 and that this is 32. Okay, so the idea is that the whole thing is equal to the sum of its parts. So the first part plus the second part equals the total. So what does that mean? The first part, so part 1 plus part 2 equals the total. That's my equation. Of course, we don't want p's and total, the word total in there. We want expressions. So you just write in your expressions. The first part is 3x minus 10. The second part is 32. and it equals the total length. So part 1 plus part 2 equals the total. That's another way that you're going to have to be able to set up equations. Okay, so that's the first goal, right, is to set up the equation. All right, that's the first kind of hurdle you'll have to get over in a lot of these geometry problems. Okay, the second thing you want to be able to do is you're going to want to be able to then solve for x or any other variable. I mean, it doesn't have to be x. X is very common. We see n a lot in geometry as well, but just solve for the variable, okay? Once you solve for the variable, you're not done. This is the part that a lot of people forget. You have to answer the question. What question are they asking? Are they asking for what is x, right? Do they say what is x? If that's the question, then you find x and you're done. If they say what is the measure of angle A, then you have to use that x to find the measure of angle A. So you'll plug it back in, right? A lot of the times we are plugging x back in. We call it back substitution, all right? They're gonna have that distractor answer. Like if you have x equals 14, right, your answer choices here for your ACT, they're gonna put 14 on there. They're gonna want you to say, oh, I got 14 and I see 14, I got it. But you gotta remember that maybe the expression for the angle was 3x plus 1, and you've gotta go back and plug in that 14 to actually get your answer of 43. So maybe 43 is right here. So that's the correct answer. They're gonna get a lot of people on that 14. They're gonna trick a lot of people because when you solve for the variable, whatever you get, they usually put that on there as kind of a distractor answer. So just be ready to set up an equation, solve for the variable, and then answer the question. Okay, that's the big one there. Make sure you answer the question. All right, so moving on. Next big thing is area and perimeter. Okay, these are kind of basic. We're going to go over them. There's not a lot to this. It does get a little more complicated towards the end, but a lot of fundamental stuff here. So just remember, this is two-dimensional. When we talk about area, we're talking about a two-dimensional object. When I say what is the perimeter, we're saying what's the perimeter of a two-dimensional object. That means it's flat, okay? Like a piece of paper or a table or something that's flat. It can be represented in a flat object, okay? Now area is kind of like how much stuff fits on the inside, okay? It's like the inside amount. So I always think about like paint. How much paint would it require to paint something, right? That's how much of the inside we have. All right, perimeter is more of an idea of the distance around the outside. Okay, it's more of a distance. So distance around the outside. So it's not really the inside, it's the distance around the outside. One way, you would think about this is just how far would it take you to walk around, or what's the total distance? So you basically just add up all the distances. So to find perimeter, add up all the sides. That's kind of the key here for perimeter. You just add up all the sides. Okay. One thing to notice, area will be given in two-dimensional. So two-dimensional units. So things like feet squared or inches squared or units squared. They'll have that unit in a feet squared because you just need 2 dimensions to talk about it. Perimeter is in one-dimensional units. So you'll see like, what's the perimeter? Oh, it's 3 feet or it's 75 miles, right? It's not miles squared, feet squared, meters squared. It's just single units, okay? All right, so there's some basic area formulas that you have to memorize. Any of these could be on the ACT. Basic ones all the way up to ones that are probably stuff you may never have thought of. And there's actually some shortcuts to ones that you know anyway, so it's good to go over this again. So let's first talk about a square. All right, we know that all 4 sides are the same and they're all 4 right angles. So the area formula is just the length of the side squared. So S is the length of the side squared. Basically, it's length times width, but since length and width are the same thing here, then it's S squared. Okay, it's like length times length. That'd be length squared. They just call it S when it's the same thing all the way around. Okay, next one would be a rectangle. Of course, in a rectangle, all 4 sides don't have to be equal. They can be, but usually they're not. You have opposite sides that are equal, and of course all the angles are 90 degrees. So the area would be length times width of a rectangle, where this is your length, your width. Sometimes you can interchange those. It doesn't really matter which one's length and which one's width. All right, next shape, parallelogram. All right, so parallelogram. You have opposite sides that are the same. It's kind of like a rectangle that sort of fell over on its side, right? It doesn't have to be all the same. It could be like a wide thing and just tilted on its side. So the formula here is base times height. So the base is the part that's kind of like sitting on the ground. Now the height here is this, I'm going to use a different color actually to show you the height. The height here is in green. It's this perpendicular, that's the height. So height is in green there. It's that perpendicular vertical line that describes the height there. So it's not the length of those diagonal sides. It's actually the vertical piece. And a lot of people get that confused, so don't make that mistake. Okay, now there is a separate formula here. You can use these diagonals. So call this diagonal 1. Now diagonal 1 has to go all the way across, okay? And diagonal 2 has to go all the way across. That's diagonal 2. So we can use a formula using just the diagonal lengths. And the formula is diagonal length 1 times diagonal length 2 cut in half. All right, and that's another way to find the area of a parallelogram, okay? So if you know the diagonals, that's a way easy shortcut, because otherwise you're using all these, trig formulas or some complicated things. That's going to save you a lot of time there. So I'm going to put a star by that. All right, there we go. There's my little star. All right, so the next formula is going to be a triangle. Now we all probably remember this one, that the area is 1/2 base times height. Base is whatever's on the ground. Now the only weird thing here is the height. The height is the vertical distance from the highest point straight down to the ground. It's got to be perpendicular, okay? Now a lot of the times we see triangles like this, okay? The height is the highest point straight down to the ground. So that's the height right there. It's not the length of this diagonal here that I'm drawing in really thick. It's not the length of that diagonal. It's the vertical height from the very top, the highest point, all the way straight down to the ground, perpendicular to the ground. Okay, now if this is an equilateral triangle, then there's a special formula, right? If all three sides are the same length, so if it's an equilateral triangle with 60-degree angles, we can say that the area of the equilateral triangle is going to be √3/4 times the side length squared. So whatever the side length is, it's all the same around, right? √3/4 side squared. That is a formula that will help you if you run into it. It's going to save you a ton of time versus using trig ratios to try to find the height. And it's a lifesaver there. So just remember that one. Put a star by that one as well. All right, next shape is a rhombus. So a rhombus is a parallelogram. So really, you just refer back to parallelogram. The only difference is all four sides are the same. It's like a square that got tilted on its side. It just kind of flopped over, okay? So a rhombus is the same as a parallelogram, base times height, where this is the base, and the height is actually this perpendicular vertical line from the highest point. Also, don't forget your diagonal trick, diagonal 1 times diagonal 2 cut in half. That's also the formula where the diagonals would be these green lines right here. The length of the diagonal times the length of the diagonal, all the way across, okay? That's another way to see that. All right, last one, trapezoid. Think of a trapezoid as any kind of triangle where you cut off the top part, right? There was this triangle here, but you cut off the top. The only thing is it has to be perpendicular. You slice it perpendicular to the base. So we call this base 1 and base 2. The area is the product of the two bases divided by 2 times the height. Okay, basically, sorry, base 1 plus base 2. It's the average of the two bases times the height. Okay, What that does is it basically takes this little triangle piece and puts it up here, rotates that over to here, kind of take this piece and move it over to here, you get this. It basically makes a rectangle where the width is the average of the two bases and the height is the height, okay? So that's kind of an explanation of why that works. So remember, the height is this perpendicular distance from the top to the bottom, just like all the other things. That's always the... All right, one more formula is the area of a circle. The area of a circle is pi r squared. So pi times radius squared, where the radius is the distance from the center of the circle to the outside. Okay, that's that last formula that we need there, circle. Also the perimeter of a circle, usually with perimeter you're just adding up a bunch of pieces, but with a circle it's a little more complicated. So what you're going to do is remember that it is pi times the diameter, or 2 pi r. Okay, either one of those is the distance around the outside. It's kind of like the perimeter, but we call it the circumference. It gives a special, circumference is the perimeter of a circle. It gets a special name because circles are special. All right, so where it gets complicated is when you have something like this. Okay, this shape, it's called a complex shape. So it's not just a basic, triangle or rectangle. Maybe it's a combination. So maybe I could add this in here to kind of reinforce that. It's a couple of different shapes put together. It's a complex shape. Well, it's not terribly difficult. All you got to do is remember to break it up into shapes that you do know the size of. Right here, that's a half of a circle. Okay, half of a circle is pi r squared. That's a full circle, but you just divide it into 2. Okay, this is a rectangle. It's length times width. There's another rectangle, length times width. Here's a triangle, 1/2 base times height, right? The base is on the ground, the height is the vertical part. You just take all 4 of these little mini equations and you add them together. So you do the first part, that's your half circle, plus your other part. So basically you just add up all these pieces and it gives you the total area. So all you got to do is add up the parts of the individual pieces, okay? All right, so what about if you have, let's say we have a circle and then we have a square that's built into the circle, and I just want to know the area of this shaded region. So a lot of the times these problems are presented as area of shaded region. So we'll say area of shaded region, all right? So these are always kind of the same idea. Basically what you want to do is you want to find the total area of the biggest piece you can. So the whole thing, right? And then you want to subtract the area that you don't want. So we don't want this area in the middle, right? If I take it away, which is subtraction, what I'm left with is just the pieces on the outside, which is what I want. So you're going to find the whole area of the big circle, and you're going to take away this inner area. You're going to take it away. You're going to say, I don't want it. And that's going to leave you with the little piece on the outside. So these kind of ideas are pretty similar. You'll always have an outer region that you can calculate, and then an inner region that you want to get rid of. You don't want to consider it. So whenever you throw it away, what you're doing is subtracting. So just remember, just take the outside minus the part on the inside that you don't want. That's going to give you the area of the shaded region, okay? So remember, this one would have been like pi r squared is the area of the big region minus whatever the length of this square is squared. This formula here kind of does it. It's the area of the big region minus the area of the inside region, okay? All right, so let's try an example here of the last 2 kind of problems that we dealt with. So let's say we've got this shape here where the height of that rectangle is 6, length of the rectangle is 4, and the base of this triangle is 4. Okay, so remember, this is half of a circle. So half of pi r squared. So pi r squared divided by 2. What's the radius? Well, the radius is just this distance right here, which is just 3. So it's pi times 3 squared divided by 2. That's this region here. We've got it covered. Okay, plus the area of this rectangle? Well, this rectangle is length 10 and height 6. So length times width, there you go, 10 times 6. Plus the region of this, it's 1/2 base. The base is 4 times the height. Remember, the height is 6. We don't see that here, but remember the height of the rectangle on the left side is 6. Therefore, the height of the right side of the rectangle should also be 6. And we just work this out. 3 squared is 9. So you get 9 pi over 2 plus 60 plus 12. So you get 72 plus 9 pi over 12. So they could say 4.5 pi plus 72. They could say 9 pi over 2 plus 72. They could multiply that out to be a decimal, right? Don't forget 9 pi over 2, it's a fraction. So you can go to alpha y equals and make a fraction. 9 pi, pi is right here. It's the second function of this caret over 2. Then you'd hit enter, you get a decimal, you add 72 to it, that would be your decimal answer, 86.13. So it just depends on how they present the answers, if they're in decimal form or if they're some kind of simplified form. Yeah, but that's the idea, right? You don't also have to do the fraction like I did here. You could just do in parentheses 9 pi divided by 2, right? And then add your 72, you get the same thing. You could also just do it without the parentheses, I think. 9 pi over 2. I think it's going to do it just right, yeah. So there's lots of ways to do 9 pi over 2. But anyway, let's work one more example here. Let's say we have a rectangle that has length 6. Let's call it a square, okay? So we have a square, length 6. We've got a circle on the inside, and I want to know the area of the shaded region, okay? Well, start with the outside. The outside is a rectangle that, or a square that's 6 by 6 that has 36 square units. Okay, so 36 is the area minus the area of the circle. Well, remember, area of the circle is pi r squared. What's the radius? That's the question here. What is this distance right here? Well, if it's 6 all the way across, it's 6 all the way across in the middle. So halfway would be 3. That would mean that radius is 3, so we get 3 squared times pi, we get 9 pi. So 36 minus 9 pi. Of course, you could make that into a decimal, but that's a lot of the times how you're going to see that answer written. So that'd be the area of that shaded region. Okay? All right. Next idea is called geometric probability. Right? We remember probability from a couple weeks ago. Geometric probability is basically when I have a region and I have like a shaded region, and I say, what is the probability that I will, if I pick a point at random, that point at random will be in the shaded region. Okay, so if I pick a point inside this circle, what's the probability it will come from the shaded region? That's the question. Okay, so usually they'll give you, this isn't a very good picture. I'm going to start over on my picture. Let's say that this is our picture. Okay. So maybe this is at the coordinate 3 and -3. We're down here at -3 and 3. Question is, what's the probability that a point chosen from inside the big circle will come from the shaded region? Okay, so first of all, we need to find the area of the shaded region out of the total area. The total area is the big circle, okay? That's easy. That's a circle with radius 3. We got a lot of 3's here for radiuses. So that's pi times radius squared, so 9 pi, right? Because radius is 3. That's the area of the total. So I'm going to divide by 9 pi here. Now the area of the shaded region, right? That's the whole big circle minus the little circle right here. So basically, I want to calculate the big circle and then subtract away the part that I don't want. So I know the area of the big circle was 9 pi minus, what's the area of this little circle? Well, what's the radius here? Looks like the diameter is 3. So I think the radius would be 1.5, right? Because it's only half that distance. So pi times the radius squared. The 1.5 squared, if you use your calculator, was 2.25. So we get 2.9 pi minus 2.25 pi. Remember, it's just like an x. 9x minus 2.25x would be 6.75x. But instead of x's, we've got a pi here. So that's the area of the shaded region. So that's the part that goes on top. 6.75 pi over 9 pi. There's a pi on top and a pi on bottom. So you get 6.75 over 9. That's the probability that a point chosen at random will be in our shaded region. So it's like the part over the whole, the shaded part over the total, okay? So just be aware that those kind of problems exist as well, but this is just basically the formula. It's the area of the shaded part, or the part that I want to select from, right? It's my very specific thing versus my total, which is just the whole circle. And that will give you the probability that a point chosen at random from inside that circle will come from the shaded region. All right. Next topic is volume and surface area. Okay. Now remember, we already talked about perimeter and area. Those were two-dimensional ideas, flat surfaces, 2 and 1 dimensional. This is going to be coming from a 3-dimensional object, like a beach ball or the globe or a box of cereal. Those have 3 dimensions to them. So with volume, well, actually, let's start with surface area. Surface area is the outside. Okay, think about paint again, right? So how much paint would it take to put on the outside of an object? So this is actually 2-dimensional. So you'll see things like surface area will be written in feet squared or meters squared or whatever, all right? The surface area is the outside of the shape. It's basically you add up all the areas of the sides of the object. So it's like you add up all the things on the outside. Just like perimeter, you add up all the things on the outside. Same thing with surface area. You're going to add up all these areas of the outside, these 2-dimensional areas. All right, so with volume, we're going to be talking about the inside. A lot of the times we think about like how much water would it hold, right? How much water would fit on the inside? That's one way we often think about it. Remember, this is a 3-dimensional idea, so you'll hear volume in terms of feet cubed, inches cubed, or meters cubed. It's going to be in some kind of unit where it's cubic units, okay? All right, one other thing I want to mention is lateral area. Lateral means side. So the area of like a cylinder, for example, has 2 bases, the top base and it has a bottom base. So the lateral area is just the area around the side. So lateral just means side area. So basically it's the area, it's the whole surface area minus the bases. So you could find the whole surface area and then just subtract away the bases to find the lateral area. Or sometimes you just find the lateral area. But just remember that that's what that means. Lateral area means the side. All right, so when you're finding volume, all right, it's pretty much the same formula each time, okay? Just you got to remember there's 2 types of shapes that you're going to deal with. You're going to be dealing with prisms, which are known as cylinders, okay? When it's a circle, when it's a circular base, right? That's the first type. So these look like this, right? This is a prism. It's like a block that's extended out, or a cylinder would look like sort of a log like that, where the base is a circle instead. It gets a special name. The other type is a pyramid, and when it's got a circular base, we call it a cone. All right, so you can kind of see these are a little hard to draw, but I could do an average job there. There's a pyramid, and of course a cone would have just a circular base. Okay, notice that the pyramids come to a point right here. So pyramids come together to a point, whereas cylinders don't. All right, so the volume of a prism or a cylinder is always the same. It's the area of the base. Okay, so here's my base here. and then this would be my length or my height. Here's my base here, and then here's my length, or what I'm going to call height. Height is if it's just sitting down, like a can of soup just sitting there. Height is the height there. So it's the area of the base times the height. Okay, now the volume in cone, same thing. It's going to be the area of the base times the height. The only difference is you divide that by 3. So it's a third of that length, or third of that volume, excuse me. Okay, so whatever the base is, remember the base could be any basic shape. So it could be a circle, in which case it's pi r squared. It could be a rectangle, in which case it's length times width. Could be a triangle, so you'd use 1/2 base times height. You use any of those area formulas that we discussed earlier. Then you just multiply that by the height. Okay, the volume is always a third of that, so you take the volume of a cylinder, divide it by 3, you'll get the area or the volume of a cone. All right, so those are the basic ideas about volume. Don't forget lateral area is the area on the side. That's definitely something they could ask on the ACT. All right, so the next thing is basically how changing a parameter will affect a formula. All right, so a parameter is just like a fancy way to say a variable. All right, so if you've got this area equals pi r squared, if I double the radius, what happens to the area? If I double the radius, what is the area now, right? A lot of people think if I double the radius, it's obviously going to double the area, but that doesn't always work, okay? So first of all, let's look at an example by plugging in numbers. You can always just test this by plugging in numbers, okay? They're usually vague in these kind of problems. They'll just say, if I double the radius of a circle, what happens to the area? They won't give you any numbers. Well, you can use numbers, okay? You can plug in your own numbers. So like, for example, you know the formula for the area of a circle is pi r squared. Let's let the radius equal 4, okay? So the area, if the radius was 4, would be 4 squared, which is 16. So usually put the number in front and say 16 pi. That would be the area if the radius was 4. So what if I doubled the radius? Okay, well, the radius would now be 8. So I'd plug it into the same formula, pi r squared. I'd get pi times 8 squared. That's 64 pi. Okay, how did that change? The 16, if it doubled, would be 32. It didn't double. It multiplied it by 4. This is 4 times as big. Okay, so how does that work? Is there an easy way to look at a formula and know how this works? Well, there is. It's all about dimension. And dimension, really, when I'm looking at dimension, that radius squared in that formula, that's a second dimension. That has a power of 2, right? That exponent there. That means it's going to double twice, okay? So you just know that when you double something that's squared, you're going to double it twice. It's going to be 4 times as big. Now, what about if you cut it in half? Would it work the same way? Yeah, you cut it in half twice. A half times a half is a fourth. It'd be a fourth as big. And we could have done that in that last example, actually, if we would have said, well, what if instead of doubling the radius, what if I say the radius is half as big? Well, I get pi r squared to be pi times 4. So 4 pi, you can see that it's 1/4 as big, because I cut it in half twice because the radius is being squared in the formula. All right, so basically here's kind of how this dimension thing works. Let's say you take a rectangle and you double the length, so you double L, right? What's going to happen to the area? The area is going to double, right? And again, you could test that by plugging in values for L and W and just seeing how it works. But since L is to the power of 1, we don't write that power of 1, but it's there, then it will work linearly. So if you double the length, it will double the area, all right? Now what if you're in a formula like a square, where it's the side squared? What if you double the length of one of the sides? Well, since it's side squared, we've got to double and then double. So I'm going to multiply it, right? I'm going to go back up here and write times 2. Double means to times 2. Well, we're going to do times 2 times 2. Right? Because it's s squared. So if I do 2s, it's going to be 2s and 2s. So that's 4 times as much. So the area will be 4 times as big if you double the length of a square. All right, what about the volume of a sphere? Right, you may not know this formula, but it's 4/3 pi r cubed. What if I double the radius of this sphere? Well, I'm going to double it how many times? 3 times. I'm going to double, double, double because it's the radius is to the power of 3. So 2 times 2 times 2 is 8. So this will be 8 times as much volume. All right, it's all about the exponent there. And now remember, it works the same way with multiplying and getting bigger. If you multiply by a fraction, like maybe it's 1/3 as big. Well, what about this formula? If I say that the length is 1/3 of what it used to be, how will that affect the area? The area will be 1/3 as big. All right, what if I plug it into this formula where there's side squared? What if I say the new side is 1/3 as big? Well, it'll be 1/3 of 1/3. Remember how we multiply that? We do top and bottom straight across. 1, 3 times 3 is 9. So it's 1/9 as much area. And again, if I plug it into the volume, if I do say the radius is 1/3 as big, it's 1/3 times 1/3 times 1/3. It's going to be 1/27 the volume as the original. Okay, so that's how changing a parameter can affect a formula. All right. All right, next thing we're going to talk about is symmetry. All right, so there's 2 types of symmetry. We have rotational symmetry. So when I rotate an object, it looks the same if I rotate it around. And then we've also got reflectional, the reflection symmetry. Okay, I realize you can't see that. So reflectional symmetry. Okay, so let's look at an object like this. All right, is there a line of reflection? Meaning, is there a line that where I draw it across, it's the same on both sides? You can see that that's not the same on both sides. What about this line? Is it the same on both sides? Almost like if you took it and you folded it in half across that line, would they overlap exactly? You can see that doesn't work. But vertically, if I fold that in half, it'll be the same thing on both sides. So that is a line of reflection. Now, when I say, does it have rotational symmetry, what I'm saying is if I take the object and I spin it around the center point, will it ever be the same? Of course, when I go all the way around, it's going to be the same. That's obvious, but we don't consider that. We say if I rotate it half of the way or 1/4 of the way, will it ever be the same? This does not have rotational symmetry. There's no rotational symmetry because if I rotate this, it never looks the same until I get all the way around and now it looks the same. That doesn't count. Okay, let's look at an object like this. Okay, you can see this one, if I rotate, that's not a great drawing. Let me try that again. All right, if I rotate this thing 180 degrees, right, if I spin it halfway around, it will end up looking like this, the same thing, right? Like if this is point A, it would rotate over here to point A prime. You can see that that thing has rotational symmetry because it looks identical to what it used to if I go part of the way around that circle. So this thing has rotational symmetry. It does have rotational. Does it have reflection? Is there a line that I can draw in here? It's tempting to say that maybe across this line, but it won't work because this point here reflects over down here, not where it should be up here. So that would not have rotational symmetry. And it's kind of, I don't know how to really teach somebody about that. You just have to kind of look at it and think, is there a way I could fold this to where it would kind of cross over exactly? This has no reflection, no reflectional symmetry. Okay, now there are objects that have both. Let's look at this equilateral triangle. If I rotate this thing 60 degrees around, right? If I rotate it 60 degrees around, it looks identical. If this is point A and I rotate it 60 degrees around, not 60, 120, I'm sorry. If I rotate it 120 degrees, then point A becomes on the top and it looks identical, right? And then I could rotate it another 120 degrees and now point A is over here on the right side, but it looks the same. Okay, so we would say this thing has rotational symmetry. But also, if I drew a line down the center here, You see how if I folded it on top of itself, that it would have reflectional symmetry. Also, it has reflectional symmetry across this line, right? If I folded it that way, or if I folded it this way. So we would say this thing actually has 3 lines of symmetry. Now remember, lines of symmetry goes with reflection, reflectional. So a lot of times when they ask, this thing has reflectional symmetry, how many lines of reflection does it have? So they could ask a question like that. And in fact, looking at a square here, how many lines of reflection does it have? Well, it's got one down the center, right? If I fold it over, that's going to be the same. Also, if I fold it vertically, it'll work, but also diagonally, right? If I fold it either way, it's going to work. So there's 1, 2, 3, 4 lines of symmetry there. So be prepared to answer questions like that about symmetry, and also just kind of understanding what rotational and what reflectional symmetries are. Okay. All right, moving on. So we're going to real quickly talk about some trig stuff. It's touched in geometry. We'll get into more detail when we get to trig on the last day of the class. But for now, we're just going to talk about the geometric ideas behind sine, cosine, and tangent. Okay. All right, so first idea is that this has to come from a right triangle. These sine, cosine, and tangents do not count if we're not in a right triangle. Okay, we have to be in a right triangle. So the idea is that if I have a right triangle, okay, and I look at one of the angles, not the 90-degree angle, okay, if I look at one of these angles, we're going to use this word theta here. That's that Greek letter theta. That's commonly used for angles here. This angle theta right here has a perspective. So from its perspective, there's an opposite side, an adjacent side, and a hypotenuse, okay? Opposite side lives furthest away across, it's like all the way opposite end of the triangle. So we would call this the opposite side as viewed from that angle theta. The adjacent side is always the one that connects the angle theta over to the 90-degree angle. And then the hypotenuse is actually always the one that's the furthest away from the 90-degree angle. It's the longest side, the hypotenuse. I wrote that wrong, hypotenuse. So I usually abbreviate it OPP, ADJ, and HYP, opposite, adjacent, and hypotenuse. Now, same triangle, right, 90-degree, it's got to be a right triangle. Now I'm looking over here at this angle. We're going to call it theta now. So from its perspective, the opposite side is not right here like it was in this triangle, right? The opposite side is now all the way across here. The hypotenuse is always going to be the same, but the adjacent and the opposite will switch sides if I switch angles, okay? So theta, again, is the angle. Sometimes you can use other letters like A or B, but usually theta is used quite often. Okay, so what is sine, cosine, and tangent? Right? What are these things? Well, what they are, they're 3 different ratios that make 3 formulas. So basically, they're each a formula that deals with the ratios of 2 sides of these right triangles. So the ratio of 2 sides of this right triangle, and the formula also deals with an angle, theta. Okay, so it's 2 sides, the ratio of 2 sides and an angle. That's what sine is. The sine is just the ratio of these two sides. The cosine is just the ratio of these 2 sides, and the tangent is the ratio of the other 2 sides. So here's how it works. The sine is the ratio, the sine of the angle, I should say. The sine of the angle is the ratio between the opposite side and the hypotenuse. Okay, remember, opposite and hypotenuse, those are side lengths. These are side lengths. And this right here is an angle. It has to have an angle in there. You can't just do the sine equals. It's got to be the sine of an angle. Okay? All right, the cosine of an angle is the adjacent side divided by the hypotenuse. Okay? It's a different ratio. And the tangent of an angle is the opposite over the adjacent. It's its own ratio of its two sides. Now, if you ever looked at it, tangent is really just the sine over the cosine. The sine, right, is opposite over hypotenuse. Cosine is adjacent over hypotenuse. If you multiply this out, if you flip by the reciprocal, hypotenuse over adjacent, you can simplify that to opposite over adjacent, which is what you get here. But just remember that tangent is also considered the sine over the cosine. Like if you knew what the sine was and you knew what the cosine was, you could figure out the tangent by just dividing those two together. Okay, so easy way to remember these three formulas is SO, CA, TOA. Everybody who's been through geometry and some algebra 2 and trig and all these classes have probably seen this thing, SOHCAHTOA. There's lots of ways to remember it. Some old hippie caught another hippie tripping on acid. I don't know why that one sticks with me, but I learned that from a fellow teacher, and she teaches it, and she said her kids always remember it. Silly, but whatever helps you remember it. So this is the first one. Sine is equal to opposite over hypotenuse, SOH. Sine is equal to opposite over hypotenuse. CA, cosine of the angle, is equal to adjacent over hypotenuse. And then TOA, the tangent, is equal to the opposite over the adjacent. Just an easy way to help you remember these. All right, so how do you solve one of these trig ratio problems? All right, I'm calling it a trig problem, but really it's just geometry. So how do you solve one of these problems? First thing you do, okay, draw and label. When I say label, I mean opposite, adjacent, and hypotenuse. Draw and label the triangle, okay? That's always the first thing. You want to draw a picture. It really, really does help. All right, second thing you want to do is set up the equation using one of your trig equations, your sine or your cosine or your tangent formulas that we just looked at, okay? Third thing you want to do is you want to solve for the unknown value. There'll always be one thing you don't know, okay? So solve for either the angle or one of the side lengths. Whatever thing you're looking for, you're just going to solve for the unknown value. Now I'm going to put a little star here. Make sure that you are in degree mode, because we're almost always talking about degrees. So on your calculator, you're going to probably use your calculator here. Go to mode, which is right here. Mode, go down and make sure you are in degree mode. Go over to degree and hit enter. Okay, if you're in radian mode, it's gonna throw you off. All right, so that's basically the three steps. Now, step number 2 is actually a little bit tricky sometimes. Which equation do I use? Do I use sine equation, or do I use the cosine equation? So which one do you use? Well, you're always going to know two things. You're going to be given two values that are known, right? They'll give you either the angle and one of the sides, or they'll give you both sides. They're going to give you two things. And there's always going to be one thing you want to know. Okay? There'll be two things that you know and one thing that you want to know. Well, whichever equation deals with the two things that you know and the one thing that you want to know, use that equation. So for example, looking back here, if they give me the opposite side and they give me the angle theta, and I want to know the adjacent. So what is the adjacent? Which one deals with opposite, adjacent, and theta? Well, sine is opposite and hypotenuse in theta, so it's not that one. Cosine is adjacent and hypotenuse in theta, so it's not that one. It's going to be tangent because it deals with opposite and adjacent and theta. It has the three things that we're looking to find or that we know, right? It's got theta, opposite, and adjacent. That's exactly what I want to use because that's what I'm looking for and what I have, okay? So that's basically the idea, using the two things that you know and the one thing that you want to know. That is how you're going to know basically which of the three formulas to use, because they're all very similar. Okay, so let's look at an example. All right, a 70-foot guide wire holds a 30-foot pole. What's the angle of inclination? So 70-foot guide wire holds a 30-foot pole. What is the angle of inclination? Well, we better talk about inclination and declination first. All right, so if you've got something like this, which is actually what we have, we've got this pole, right? We got this guide wire. The angle of inclination is right here. I'm going to actually do this in a purple color here so you see it. That's the angle of inclination, is what I have in purple. It's basically the angle from the ground up to the guide wire. That's what we call inclination. Okay. If I were to have a similar idea where there's maybe a plane flying above here, there's a great artistic rendering of an airplane. What is the angle of declination? Well, that would be this angle going down. Okay. So this would be the angle of declination. If you were to see these words, you'd want to know what they meant. Declination goes down from the horizontal here, down. Inclination goes from the horizontal up. All right. So that's that idea. So what we've got is this guide wire that's 70 feet long. We've got a 30-foot pole. The question is basically, what is the angle theta right there? What is that angle? Okay. So remember, first thing we do is draw a picture, right? Then I label things. So I label opposite side, adjacent side, and hypotenuse. Now, which one do we not care about? I don't care about the adjacent side, really. Okay. I just care about opposite and hypotenuse because those are given to me. Those are known values. And I care about theta because it's what I want to know. I don't really care about the adjacent side. So which of those three formulas deals with hypotenuse and opposite? Let's see. Sine was opposite over hypotenuse, so it's sine. So we're going to use the formula sine of the angle equals the opposite over the hypotenuse. Okay? Then you plug in what you know. So plug in theta. Well, we don't know theta, so we just leave it as sine of theta equals opposite, which is 30, over hypotenuse, which is 70. And then all you got to do is solve that formula. And I'm going to show you how to solve that formula. Okay? So the first thing is you got to set it up, and then you got to solve. So you're going to plug in what you know, and then you're going to solve it. Okay? So there's three types, there's three cases, I guess I could say, of setting up and solving these types of trig formulas, okay? The first case is that you don't know theta, right? That's the example that we just looked at, right? If you go back to this, we don't know theta in the formula, right? I've got sine of theta equals 30 over 70. I don't know what theta is, so we're talking about that case right now. So as an example, we could have the formula be sine theta equals 30 over 70. Okay, so how do we get theta by itself? We got to get rid of sine. You don't divide by sine, okay? The sine and the theta are stuck together. The only way to undo it is to use the inverse operation of sine. The inverse operation of sine is called sine inverse, and it's on your calculator, okay? See how sine is right here? Well, sine inverse is the second function of sine. It's this little blue sine to the -1. That's sine inverse, okay? Now here's how it works. Let's do the sine inverse of the sine of something weird, 25.369, something weird, all right? The sine inverse of the sine of something weird is something weird. So see how it's like the sine inverse and the sine just came together and disappeared and left us with that thing? That's how we're going to utilize that. So what we're going to do is we're going to take the sine inverse of the left side, and we're also going to take the sine inverse of the right side. Okay? Remember how sine inverse of sine of something weird left us with something weird? Well, this is the sine inverse of the sine of theta. It's just going to leave us with theta. Basically, those inverse operations go away. Okay? That leaves us with the sine inverse of 30/70ths. Well, just use a calculator here. All right? Use a calculator right here. Make sure you're in degree mode. Right, are we in degree mode? Go to mode, make sure you're in degree mode, not radian mode. We're good to go there. Okay, so then I use my calculator. So sine inverse of 30 over 70. 25.376. Okay, that means that the angle is 25.376. 25.377. If I want to round to 3 decimal places, I better say 377. Or 2 decimal places would be 38. We'll just round it to 2 decimal places. Okay, so if you don't know theta, You basically take the sine inverse, or if it's cosine, you take the cosine inverse. If it's tangent, whatever your formula says. If it says cosine theta equals 1/6, well, then you do cosine inverse of both sides. And remember, that will cancel. You'll get this thing here, which you just use your calculator to find. If you had the tangent of theta equals 9/8, well, then you would do tan inverse of both sides. That tangent inverse will cancel with the tangent and leave you with this thing, tangent inverse of 9/8, which you just use your calculator to find. It'll tell you the angle, okay? So those are all here under sine, cosine, and tangent. You see those second functions, they're all right there. All right, that's the first case, if you don't know theta. Okay, the second case is that you don't know the numerator. Remember, numerator is the top, denominator is the bottom. So we do not know the numerator or the top. So we would have, an example would be, I have a triangle here with 40 degrees, and we've got this unknown value, and then the hypotenuse is 105 feet, okay? So which do we know here? We have the opposite, which we don't know. We don't know the adjacent, but we want to know the adjacent, and we have the hypotenuse, which we know. We don't care about opposite. Adjacent and hypotenuse, that's cosine, right? Adjacent over hypotenuse. So fill in what you know. We know the angle is 40, okay? We know the adjacent is unknown, and we know the hypotenuse is 105. So this is this case where you don't know the numerator. You don't know the top, okay? This is really easy. All you got to do is multiply out the bottom. Multiply by 105. 105 cancels on the right and leaves you just with x. Over here, you get 105 times the cosine of 40. Now, don't multiply that 105 into the 40. Don't try to say it's cosine 40 times 105. That is not how it works. Don't do that. Multiply it over on the left. It's got to be out front. Okay? Now, how do we find this? Anybody know the cosine of 40? I don't. So we just use our calculator. Okay? Go over to our calculator, type in 105 times cosine of 40. Now, if we're in radian mode, this answer will be not correct. But since we're in degree mode, it's good. It's 80. So that tells me in this picture that this is 80.43 feet. Since this was in feet, this is in feet. So the length there to make a 40-degree angle and make it all work, that's got to be 80.43 feet. Okay, third case, if you don't know the denominator. Okay, remember that's the bottom. So for an example, right, I've got this, let's say theta's up here this time, and it's 60 degrees, okay? And I know that this is 98 inches. The question is, how tall is this thing, okay? So what am I dealing with? Well, let's label it first. Here's my opposite, right, because it's all the way across here. This would be my adjacent, and then, of course, my hypotenuse is across from the 90-degree angle, which is right here. So I don't care about the hypotenuse. I just care about finding the adjacent. I know the opposite, and I know the angle. Opposite and adjacent, that's going to be tangent. So the tangent of the angle is the opposite over the adjacent. So fill in what you know. Well, we know that it's the tangent of 60 degrees because the angle is 60. We know the opposite is 98 inches, but we do not know the adjacent side. Okay, so this is our case where we don't know the denominator. All right. Now, so many people try to just divide by 98. And you could do that, but it just doesn't help you out. We want to get the variable by itself, right? Problem is when there's a variable in the bottom of a fraction, we've got to get it out of the bottom of a fraction. We never deal with it in the bottom. We got to get it out. So what I actually do here is multiply both sides by x, right? I know that seems kind of weird, but you got to do it. That cancels the x there on the right side. Leaves us with x times tangent of 60 equals 98. Now, I got to get x by itself. Now it's at least in the top. It's not in the denominator of a fraction. It's where it should be. So now I just divide out the tangent of 60 on both sides. Okay, cancels here. I get x is equal to 98 divided by tangent of 60. Now, tangent of 60, some people actually know that off the top of their head. I'm going to pretend that I don't, so I'm going to use my calculator. So I'm going to get out here and do 98 divided by tangent of 60. And I'll just do it real quick. 98 divided by the tangent of 60. Now make sure you're in degree mode, otherwise this won't make any sense. 56 is our answer. That means this is 56 point whatever inches tall. Okay, now there is a shortcut here. All right, if you're in case 3 where you don't know the denominator and you get to write here, I have to rewrite it here. Tangent of 60 equals 98 over x. Notice how this became this. What do you notice there? It looks like the x was on the right, now it's on the left. The tan was on the right, now it's on the left. They sort of switch sides. That's all you got to do, right? If you don't know the denominator, you take the denominator and the x here and you just switch places. Flip-flop them, okay? It's a shortcut. If you don't like the shortcut and feel like you're going to mess up, don't use it. But that's a really, really easy thing to do. So an example would be if I knew that the tangent of 28 degrees was equal to 36 over x, all I do is switch these two because I don't know the denominator. X is 36 over tan 28. Use my calculator there to find it. Quick shortcut, okay? So that shortcut can come in pretty handy. That's all I'm going to talk about today with as far as the sine, cosine, and tangent. We will revisit it when we get to trig stuff because there's a little more to it than that. But that's the basic geometric idea, is that when you have a triangle and you know two sides and want to find an angle, or if you know an angle and a side and you want to find the other side, you use these trig identities. So just one real quick thing. Pythagorean theorem. A squared plus B squared equals C squared. Okay, we're going to talk about it next time. That's dealing with 3 sides only. So in this case, if you know 2 sides and you want to find a 3rd side, you can use Pythagorean theorem. With sine, cosine, and tangent, right? It's the whatever sine, cosine, whatever an angle equals a side over a side. So this deals with 2 sides and an angle. So you got to see the difference here. If you're dealing with 2 sides are known, 1 side you want to know, you use Pythagorean theorem. If you know 2 sides and you want to find an angle, use sine, cosine, tangent. Or if you know 1 side and an angle and you want to find the other side, right? But if you're dealing with what you know and what you want to know is 3 sides, use Pythagorean theorem. If what you want to know and what you know is 2 sides and an angle, use sine, cosine, and tangent. They're similar, a little bit different there. So that's all I got for today. Appreciate you guys being here, and we'll see you next time.